Welcome to Late Space. I'm glad you found your way here tonight. Perhaps the day has worn you down, or maybe you simply enjoy drifting off while contemplating the infinite depths above. Whatever brought you here, this moment is yours. Let yourself settle in. Release the tension in your shoulders. Allow your breathing to find its natural rhythm. Tonight, we're embarking on a journey through space and time, through mysteries both solved and unsolved, through the silent immensity that surrounds our small blue world. We'll wander gently from one cosmic wonder to the next. Some will amaze you, others might simply wash over you like waves against a shore, and if somewhere along the way, these quiet explorations guide you toward rest, that's exactly as it should be. Feel free to leave a like if this helps you find peace. It helps others discover this place too. Now, if you're comfortable, let's drift outward into the cosmic ocean. The speed of darkness. When we think about space, we often think about light. But darkness has its own story to tell. Darkness doesn't need to travel because it's already everywhere, waiting. When a star suddenly dies, when a supernova fades, darkness doesn't rush in to fill the void. It was always there. Light is the visitor, the temporary guest pushing back against an eternal night. In deep space between the galaxies, the darkness is so complete that if you were there, you wouldn't see your hand in front of your face. No scattered city lights, no reflected moonlight, no glowing nebulae. Just pure ancient darkness. The kind that has existed since before the first stars ignited. Darkness is patient. It doesn't move because it doesn't need to. It simply waits for the light to leave. Neutron stars are mountain-sized. We often hear that neutron stars are incredibly dense, but the scale is hard to grasp. Consider this. If you could somehow scoop up a mountain from Earth, something the size of Mount Everest, and compress it, until all the empty space between atoms disappeared, until the very structure of matter collapsed, you'd end up with something the size of a sugar cube. That sugar cube would contain the entire mass of that mountain. Neutron stars have compressed their entire mass this way. What was once a star larger than our Sun now exists as a sphere barely 20 kilometers across. The gravity at the surface is so intense that if you dropped an object from 1 meter high, it would hit the ground at several million kilometers per hour. Time itself moves differently there, slowed by the crushing weight of space-time bent almost to its breaking point. The cosmic desert between galaxies. When you look at images of deep space, you see galaxies everywhere, bright spirals and elliptical clouds scattered like jewels. But those images are deceptive. The spaces between those galaxies are vast beyond imagination. If our Milky Way were the size of a dinner plate, the nearest major galaxy, Andromeda, would be another dinner plate about 10 feet away, but most galaxies are much farther apart than that. In these intergalactic voids there's almost nothing. A few stray atoms per cubic meter perhaps. The occasional rogue star flung out from its home galaxy by gravitational chaos. These regions are colder than any freezer, darker than any cave. They're the loneliest places in the universe, and they make up most of space. The bright galaxies we see are just tiny oases in an infinite desert of emptiness. Stars form in darkness. Stars are born in the darkest places, in vast molecular clouds, regions so thick with dust that no light penetrates. Gravity begins its slow work. Over millions of years, these clouds collapse inward, growing denser and hotter. The process is violent on cosmic scales, but appears gentle from a distance. Turbulence ripples through the gas. Magnetic fields twist and compress. And eventually, in the heart of this darkness, pressure and temperature rise enough for nuclear fusion to ignite. Suddenly a star is born. Its light pushes outward, clearing away the cocoon of dust and gas. But that first light doesn't travel far. It's absorbed and re-emitted countless times, bouncing around inside the stellar nursery. It can take hundreds of thousands of years for a photon created in a star's core to finally escape into space. The light we see from young stars is ancient, having spent millennia trying to find its way out. The universe hums at a frequency we cannot hear. Space is often described as silent because sound needs a medium to travel through, and space is mostly empty. But that doesn't mean the universe is without sound. It's just that the sounds are far below what human ears can detect. Supermassive black holes, for instance, emit pressure waves into the thin gas surrounding them. These waves are sound, just pitched unimaginably low. The black hole at the centre of the Perseus galaxy cluster produces a note about 57 octaves below middle C. If you could hear it, it would be the deepest bass tone imaginable, a vibration more felt than heard. This note has been playing for hundreds of millions of years, a cosmic drone reverberating through intergalactic space. The universe, it turns out, has its own music. We've just never been able to hear it. Your body contains atoms from distant galaxies. Every atom in your body, the carbon, the nitrogen, the oxygen, was forged inside a star. But not all of those stars were in the Milky Way. Galaxies collide and merge. Stars are flung across intergalactic space. Supernova explosions scatter elements far and wide. Over billions of years, these atoms travel unimaginable distances, drifting through the void, eventually finding their way into new clouds of gas. Some of those clouds became our solar system, and some of those atoms became you. There's a non-zero chance that atoms in your body originated in a galaxy millions of light years away. You're literally made of the universe, assembled from pieces that have journeyed across space and time. When you look up at the stars, you're not just observing the cosmos, you're looking at distant relatives. Time moves slower. Near massive objects. Einstein taught us that time isn't absolute. It's flexible, malleable, dependent on gravity and motion. Near a massive object like a neutron star or black hole, space-time curves so dramatically that time itself slows down. If you could orbit close to such an object and then return to Earth, you'd find that less time had passed for you than for everyone else. This isn't science fiction, it's measurable reality. GPS satellites have to account for this effect. They orbit high above Earth where gravity is slightly weaker, so their clocks run slightly faster than clocks on the ground. Without correction, GPS would become inaccurate within minutes. Time doesn't flow at the same rate everywhere. It pools and eddies around mass like water around rocks in a stream. Empty space weighs something. Quantum physics tells us that what we call empty space isn't truly empty. It's filled with virtual particles, fleeting bursts of energy that appear and vanish in fractions of a second. These quantum fluctuations aren't just theoretical. They have measurable effects. They create a kind of pressure, a weight to nothingness itself. This vacuum energy might explain dark energy, the mysterious force accelerating the expansion of the universe. The more space there is, the more vacuum energy exists, pushing galaxies apart faster and faster. It's a strange concept. Emptiness has mass. Nothingness has weight. The void between stars isn't just absence. It's a subtle presence, quiet but persistent, shaping the destiny of everything. The oldest known star is nearly as old as the universe. A star called Methuselah, officially designated HD 140283, appears to be almost as old as the universe itself. Measurements suggest it's around 14.5 billion years old. But there's a problem. The universe is only about 13.8 billion years old. This is called the Methuselah paradox. Of course, the measurements have uncertainty ranges, and refined calculations have brought the star's age down slightly, but it remains uncomfortably close to the age of the universe. This ancient star formed when the cosmos was still in its infancy, when there were almost no heavy elements, when the first generations of galaxies were just beginning to assemble. It has witnessed nearly the entire history of everything, and it's still burning, still shining, a fossil from the dawn of time. Supernova remnants paint space with light. When a massive star explodes, it doesn't just disappear. It leaves behind an expanding shell of debris, gas, and dust enriched with heavy elements. These supernova remnants spread outward for thousands of years, glowing in various wavelengths as the shock wave heats the surrounding interstellar medium. Some remnants, like the Crab Nebula, are beautiful tangled filaments of light. Others are faint and diffuse, barely visible against the background stars. But all of them tell the story of stellar death and rebirth. The elements scattered by these explosions seed new generations of stars and planets. The iron in your blood, the calcium in your bones, the gold in any jewelry you might wear, all were created and distributed by supernova long ago. These cosmic fireworks are more than just spectacles. They're the reason complex chemistry, and therefore life, became possible. Planets exist in the space between stars. Not every planet orbits a star. Some were formed in the usual way, coalescing from the disk of material around a young star, but were then ejected by gravitational interactions with other planets or passing stars. Others might have formed differently, condensing from the same clouds that form stars but never quite growing large enough to ignite. These free-floating or rogue planets drift through the galaxy alone, unbound to any star. They're dark and cold, with no sun to warm them. Any moons they might have would never see a sunrise. Yet they exist, perhaps in vast numbers. Some estimates suggest there could be billions of rogue planets in the Milky Way alone, silent wanderers in the space between stars. Each one is a world unto itself, untethered, forever night. Galaxies can steal stars from each other. When galaxies pass close to one another, their gravity doesn't just affect their overall motion. It can reach in and pluck out individual stars. These tidal forces stretch and distort the galaxies, creating long streams of stars called tidal tails. Some of these stars are flung out into intergalactic space, no longer bound to any galaxy. The Milky Way is currently consuming several smaller galaxies, slowly pulling them apart and absorbing their stars. The process is gentle by cosmic standards, taking hundreds of millions of years, but from the perspective of those stolen stars, their entire galactic home is being dismantled around them. They'll eventually become part of the Milky Way, adopted citizens of a new galactic nation, their origins eventually forgotten. Light can get trapped, going in circles. Near a black hole, space-time is so warped that light can be trapped in an orbit. There's a region called the photon sphere, where light can travel in a circular path around the black hole without falling in or escaping. If you could somehow position yourself at this exact distance, you could theoretically see the back of your own head, as light from behind you would curve around and return. Of course, this is purely theoretical. The photon sphere is unstable. Any small perturbation would send the light either spiraling inward to the event horizon or escaping to infinity. But the mathematics allows it. In the extreme environment near a black hole, even light, which always travels in straight lines through flat space, must bend to follow the curves of space-time. The Milky Way will collide with Andromeda. In about 4 billion years, our galaxy and the Andromeda galaxy will collide. This isn't a collision in the traditional sense. Stars are so far apart that it's unlikely any will actually hit each other. Instead, the galaxies will pass through each other, their gravity pulling and distorting their shapes. Stars will be flung onto new orbits. Gas clouds will collide, triggering bursts of new star formation. Eventually, over billions of years, the two galaxies will merge into a single, larger elliptical galaxy. The night sky during this collision will be spectacular. Andromeda will grow larger and larger until it spans the entire sky. New stars will ignite in brilliant clusters. The shape of the familiar constellations will change as the sun gets thrown onto a new path. But by then, the sun will be nearing the end of its life anyway. This cosmic dance is inevitable, already in slow motion. Dark matter might not be matter at all. We call it dark matter because we can't see it and it doesn't interact with light. We know it exists because galaxies rotate faster than they should based on visible matter alone. Galaxy clusters hold together with more gravity than their visible mass can provide. But what if dark matter isn't actually matter in the traditional sense? Some physicists wonder if what we're seeing isn't invisible particles, but rather a flaw in our understanding of gravity. Maybe gravity behaves differently on galactic scales than we think. This idea is called modified Newtonian dynamics, or MOND. It's controversial and doesn't explain all observations, but it reminds us that we're still learning. The universe keeps secrets, and dark matter, or whatever it really is, remains one of the deepest. Some galaxies have multiple supermassive black holes. We usually think of each galaxy having one supermassive black hole at its centre, but when galaxies merge, their central black holes eventually spiral toward each other. Before they merge, the galaxy temporarily has two supermassive black holes, sometimes three or more if it's been particularly collision-prone. These black holes orbit each other, gradually losing energy through gravitational waves until they finally merge in a catastrophic event. The resulting gravitational wave burst is among the most powerful events in the universe. We're just beginning to detect these mergers, listening to the ripples in space-time as black holes millions or billions of times the sun's mass collide and become one. Stars can be banished from galaxies. Sometimes a star gets too close to a supermassive black hole. Instead of being consumed, it can be flung outward at incredible speed, fast enough to escape the galaxy entirely. These hypervelocity stars race through intergalactic space at hundreds or even thousands of kilometers per second. We've detected several of these stellar exiles. They're rare, but they exist. Stars that were in the wrong place at the wrong time, given enough kinetic energy to leave their home galaxy forever. They'll spend the rest of their lives crossing the void between galaxies, lone travelers in the dark, never to return. The universe's first molecules were simple. After the Big Bang, the universe was too hot for atoms to form. As it cooled, protons and electrons combined to create the first hydrogen atoms. A few 100,000 years later, conditions were right for the first molecules to form. The very first was probably a helium-hydrogen molecule, HEH+. Not long after, molecular hydrogen H2 formed. These simple molecules changed everything. They allowed gas clouds to cool more efficiently, which allowed gravity to pull those clouds together into the first stars. Without molecules, the universe would have remained a thin, hot soup of atoms. Chemistry began with these simple partnerships, and from chemistry came stars, planets, and eventually life. The entire story of complexity in the universe traces back to two atoms finding each other in the cosmic dawn. Pulsars are the universe's most precise clocks. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like lighthouse beams. If Earth happens to lie in the path of the beam, we detect regular pulses of radiation. Some pulsars rotate hundreds of times per second, with such precision that they rival atomic clocks. Astronomers use pulsars as cosmic timekeepers. Their regularity is so perfect that tiny variations can reveal gravitational waves passing through space or the presence of planets orbiting the pulsar. The fastest known pulsar spins 716 times per second. It's a ball of neutrons, 20 kilometers across, rotating so fast its equator moves at a significant fraction of the speed of light, and yet it keeps time with near-perfect accuracy. The hottest stars are blue, not red. It might seem intuitive that red stars would be the hottest since red is associated with heat and fire. But in reality, it's the opposite. Red stars are the coolest, with surface temperatures around 3000 Kelvin. Our Sun, which appears yellow-white, is around 5800 Kelvin. Blue stars are the hottest, with surface temperatures exceeding 30,000 Kelvin. This is because as objects get hotter, the peak wavelength of light they emit shifts toward the blue end of the spectrum. It's called Wien's law. The hottest stars burn bright blue, consuming their fuel at prodigious rates. They live fast and die young, often exploding as supernovae after just a few million years. Meanwhile, dim red dwarf stars can burn for trillions of years, outlasting everything else in the universe. Cosmic rays constantly bombard Earth. Right now, as you read this, high-energy particles are striking the Earth from space. These cosmic rays are mostly protons, atomic nuclei accelerated to nearly the speed of light by supernovae, black holes, or other violent cosmic events. When they hit Earth's atmosphere, they create showers of secondary particles that rain down to the surface. Most are harmless, stopped by the atmosphere or deflected by Earth's magnetic field. But occasionally a particle makes it through and passes right through you. You've been hit by cosmic rays countless times in your life without ever noticing. These particles are messengers from distant corners of the galaxy, carrying stories of exploded stars and colliding neutron stars, stories written in their energy and direction. Black holes can have hair. For decades, physicists believed in the no-hair theorem, which states that black holes are remarkably simple objects. They have only three properties: mass, charge, and spin. Everything else, the hair, is lost when matter falls in. But recent theoretical work suggests black holes might retain some information after all, stored in subtle distortions of their event horizon. This hair doesn't look like anything we'd recognize. It's encoded in the quantum properties of the black hole's boundary. The implications are profound, potentially resolving the black hole information paradox, a conflict between general relativity and quantum mechanics. Black holes, it turns out, might remember more than we thought. Even the darkest objects in the universe can't completely erase the past. Space. Smells like burning metal. Astronauts who have performed spacewalks report that when they return to the airlock and remove their helmets, they notice a distinct smell. They describe it as metallic, like welding fumes or burnt steak. The smell doesn't come from space itself. Space is a vacuum. Instead, it comes from atomic oxygen and other particles that cling to the spacesuit. These particles are created by the sun's radiation, breaking apart molecules in the thin upper atmosphere. They're highly reactive, bonding with the spacesuit material. When brought inside, they react with the air and moisture, releasing that distinctive smell. It's the smell of space, or at least the closest we can get to it, the scent of the sun's fury and the edge of our atmosphere. Every point in the universe is the center. It's tempting to imagine the universe expanding from a central point, like a balloon inflating. But that's not quite right. Every point in the universe is expanding away from every other point. There is no center. If you were in a distant galaxy looking back at us, you'd see galaxies receding in all directions just as we do. You'd think you were at the center too. This is because the expansion isn't happening in space. It's space itself that's expanding. There's no edge, no center, no outside. Every observer, regardless of location, sees the same general pattern, a universe expanding uniformly around them. It's a perspective that's both humbling and strange. We're all at the center, and none of us are. The sun loses 4 million tons of mass every second. The sun generates energy through nuclear fusion, converting hydrogen into helium. Einstein's famous equation E equals mc squared tells us that mass and energy are equivalent. When the sun fuses atoms, a tiny amount of mass is converted into a tremendous amount of energy. That energy radiates out into space as light and heat. 4 million tons of mass disappear this way every second. It sounds like a lot, but the sun is massive, about 2 times 10 to the power of 30 kilograms. At this rate, it will take billions of years to run out of fuel. By then, it will have converted only a tiny fraction of its total mass into energy. But that small fraction is enough to power life on Earth for billions of years. Our existence depends on the sun's slow self-consumption. Dead stars can steal life from living ones. White dwarfs are the remnants of stars like our Sun, dense cores left behind after the outer layers have been shed. Normally, they just cool slowly over billions of years, but if a white dwarf is part of a binary system with a companion star, something more dramatic can happen. The white dwarf's intense gravity can pull material from the companion star. This stolen gas spirals down onto the white dwarf's surface, where it accumulates. Eventually, conditions become right for a thermonuclear explosion, a nova. The white dwarf temporarily flares bright as the accumulated material ignites. These novae can repeat, with the white dwarf stealing more gas and exploding again. It's a cosmic vampire feeding on its companion, prolonging its luminosity long past when it should have faded into darkness. There are regions of space where time has no direction. In the extreme environment just outside a black hole's event horizon, space-time becomes so distorted that time and space swap roles. Inside the event horizon, all paths lead toward the singularity. Moving toward the center isn't a choice of direction in space, it's moving forward in time. Escaping would require moving backward in time, which is impossible. This strange region where the future is a place rather than a time is one of general relativity's most mind-bending predictions. It suggests that our intuitive understanding of time as something separate from space completely breaks down in extreme conditions. Time, like space, can be warped, twisted, and even turned inside out by gravity. Jupiter protects Earth from asteroids. Jupiter's immense gravity acts as a cosmic shield for the inner solar system. Its gravitational field deflects or captures many asteroids and comets that might otherwise cross Earth's orbit. Some of these objects are flung out of the solar system entirely. Others are captured into orbits around Jupiter itself, eventually colliding with the giant planet. We've witnessed this protection in action. In 1994, comet Shoemaker-Levy 9 broke apart and collided with Jupiter, leaving dark impact scars visible from Earth. Without Jupiter, Earth would likely be hit by large asteroids far more frequently. Life on our planet owes a debt to this giant guardian, quietly sweeping up cosmic debris that could otherwise cause catastrophic impacts. The shadows of black holes are larger than the black holes. When we see an image of a black hole, like the famous image of M87's black hole, we're not actually seeing the black hole itself. We're seeing its shadow, the region from which no light can escape. But due to the warping of space-time, this shadow appears larger than the black hole's actual event horizon. Light that passes close to the black hole is bent by gravity, creating a dark region that's about 2.6 times larger than the event horizon. This shadow is surrounded by a bright ring of light, photons that just barely escaped being captured. The image is surreal, a silhouette carved out of light by gravity so intense it bends reality itself. Stars can be square. Well, not exactly square, but close. Rapidly rotating stars can become so distorted by their spin that they take on unusual shapes. At extreme rotation speeds, a star can become a blade, flattened at the poles and bulging at the equator. In the most extreme cases, the star can develop distinct corners where the equator meets the polar regions. These stars are incredibly rare and exist at the edge of what's physically possible. Spin them any faster, and centrifugal force would tear them apart, but at this critical point they maintain a shape that's decidedly unstar-like, more resembling a squashed box than a sphere. The universe, even in something as familiar as a star, can surprise us with its variety. The universe may be flat. When cosmologists talk about the shape of the universe, they don't mean its physical outline, they mean the geometry of space-time itself. General relativity allows three possibilities. The universe could be closed, positively curved, like the surface of a sphere, open, negatively curved, like a saddle, or flat, zero curvature. Measurements of the cosmic microwave background suggest the universe is very close to flat. This means that parallel lines remain parallel forever, and the angles of a triangle add up to exactly 180. degrees. A flat universe is also infinite in extent and will expand forever. It's a strange realization. The universe we inhabit, for all its richness and complexity, is geometrically the simplest it could possibly be. Shooting stars aren't stars. When you see a shooting star, you're not seeing a star at all. You're seeing a meteor or a small piece of rock or dust burning up as it enters Earth's atmosphere at high speed. Most meteors are tiny, no bigger than a grain of sand, but they're moving so fast, often 70 kilometers per second or more, that friction with the atmosphere heats them to incandescence. The resulting streak of light lasts only a second or two. By the time you see it, the object has already been vaporized. The light you see is the meteor's final moment, its swan song as it disintegrates high above your head. It's a reminder that space isn't empty. Even Earth's path through the solar system is littered with debris, remnants of comets and asteroids. There are galaxies we'll never be able to visit. Due to the accelerating expansion of the universe, there are galaxies so far away that we'll never be able to reach them, even if we could travel at the speed of light. The space between us and them is expanding faster than light can cross it. These galaxies are beyond what's called our cosmic event horizon. We can still see them, or rather we can see where they were billions of years ago, when they emitted the light now reaching us. But any light we send toward them today will never arrive. They're beyond our reach, forever receding into the unreachable distance. Most of the universe falls into this category. Most of existence is permanently off limits. The universe has a preferred direction. For years, cosmologists assumed the universe was isotropic, looking the same in all directions. But careful measurements of the cosmic microwave background have revealed a slight asymmetry. There's a cold spot and a preferred direction, an axis, along which the universe seems to have subtle differences in temperature and expansion rate. This is deeply puzzling. The universe should be smooth and uniform on the larger scales. The existence of a preferred direction suggests either a flaw in our measurements, a previously unknown aspect of cosmology, or even the influence of something beyond our observable universe. It's a small anomaly, but it hints that the universe might hold deeper secrets than we've yet discovered. The Earth's rotation is slowing down. Earth's rotation isn't constant. Tidal forces from the moon are gradually slowing our planet's spin. Each day is getting longer by about 1.7 milliseconds per century. It doesn't sound like much, but over geological timescales the effect is substantial. A day during the time of the dinosaurs was about 23 hours long. As Earth slows, the moon slowly drifts farther away, moving about 3.8 centimeters farther from Earth each year. This dance between Earth and moon has been going on since the moon's formation, and it will continue until eventually, far in the future, Earth and moon become tidally locked, always showing the same face to each other, rotating in perfect synchrony. Supermassive black holes formed. Quickly quasars, extremely bright galactic nuclei powered by supermassive black holes, have been observed from when the universe was less than 1 billion years old. But this poses a problem. How did black holes millions or billions of times the sun's mass form so quickly? Black holes grow by consuming matter or merging with other black holes, but these processes take time. There simply hasn't been enough time for them to grow from stellar mass black holes to supermassive ones. This suggests that either they had a head start, forming as large black holes directly from collapsing gas clouds, or that they grew much faster than we think possible. The early universe was clearly a more dynamic, violent place than we sometimes imagine. Galaxies have magnetic fields. It's easy to think of space as mostly empty, but it's laced with magnetic fields. Entire galaxies are threaded with magnetic field lines, generated by the motion of charged particles and ionized gas. These fields are weak by everyday standards, thousands of times weaker than a refrigerator magnet, but they span enormous distances. Galactic magnetic fields influence the motion of cosmic rays, shape the structure of interstellar gas clouds, and may play a role in star formation. They're remnants of the galaxy's formation and evolution, shaped by supernova explosions, rotating stars, and the galaxy's overall spin. Even in the vastness of space, invisible forces connect everything. Some stars blink on and off. Certain variable stars undergo dramatic changes in brightness, dimming and brightening by factors of thousands or more. Our Coronae Borealis stars, for instance, are normally bright but occasionally fade dramatically as clouds of carbon dust form in their outer layers, blocking their light. The star effectively blinks off for weeks or months before the dust disperses and it brightens again. These stars are rare and poorly understood. They seem to be the result of two white dwarfs merging, creating an unstable star rich in carbon and poor in hydrogen. The periodic dimming is unpredictable, happening at irregular intervals. It's as if the star has clouds passing across it, but those clouds are part of the star itself, vast sooty veils forming and dissipating in the stellar wind. The solar system is mostly empty space. If you scaled the solar system down so that the Sun was the size of a basketball, Earth would be a tiny ball bearing about 25 meters away. Jupiter would be about a marble 130 meters distant. Neptune would be more than a kilometer away, and the nearest star would be thousands of kilometers off. The solar system, despite containing 8 planets, countless moons, asteroids and comets, is almost entirely empty. The distances between objects are so vast that travelling from world to world requires crossing oceans of vacuum. Even within the asteroid belt, asteroids are so far apart that spacecraft can pass through without any significant risk of collision. Space truly lives up to its name. White dwarfs will become black dwarfs. Eventually, trillions of years from now, white dwarfs will cool completely. They'll radiate away all their residual heat and become black dwarfs, cold, dark remnants made of crystallized carbon and oxygen. These objects will be among the longest lasting in the universe, persisting essentially forever unless proton decay or some other exotic process eventually dismantles them. But the universe isn't old enough yet for any black dwarfs to exist. Every white dwarf we see is still glowing, still radiating heat from its formation. They're like coals from a fire, still warm even after the flame has gone out. In the far future, they'll be the tombstones of stars, dark markers in an even darker cosmos. The Oort cloud surrounds the solar system far beyond Neptune. At the edge of the Sun's gravitational influence lies the Oort cloud. It's a vast spherical shell of icy objects, potentially containing trillions of comets. These objects are the remnants of the solar system's formation, bodies that never coalesced into planets and were flung outward by gravitational interactions. The Oort cloud extends from about 2,000 to 100,000 astronomical units from the Sun. That's nearly 2 light years. Occasionally a passing star or gravitational disturbance nudges one of these icy bodies inward, sending it falling toward the Sun as a long-period comet. The Oort cloud is a cosmic reservoir, a frozen archive of the solar system's early days. Brown dwarfs are failed stars. Brown dwarfs occupy the fuzzy boundary between planets and stars. They're more massive than planets, at least 13 times Jupiter's mass, but not massive enough to sustain hydrogen fusion in their cores. They glow faintly from the heat of their formation and from fusion of deuterium, a heavy isotope of hydrogen, but this process doesn't last long. Brown dwarfs slowly cool and fade, eventually becoming invisible in optical light, detectable only in infrared. They're common in the galaxy, but easy to miss. Some may have planets around them, others drift alone. They're neither star nor planet, occupying their own category, quiet reminders that the universe doesn't always fit neatly into our classifications. Galaxies form along filaments of dark matter. The large-scale structure of the universe resembles a web. Galaxies cluster along thread-like filaments, with vast voids in between. This cosmic web is shaped by dark matter. Computer simulations show that dark matter forms a scaffolding, with ordinary matter falling into the gravitational wells created by dark matter filaments. Over billions of years, gas flows along these filaments, collecting in the densest regions and forming galaxies. The pattern emerges naturally from gravity acting on slight density variations in the early universe. It's a reminder that the visible structures we see, the galaxies and clusters, are just the bright parts of a much larger, mostly invisible framework. The first galaxies were small and irregular. Today's galaxies are majestic spirals and smooth ellipticals, but the first galaxies were chaotic, irregular clumps of stars and gas. They were smaller, messier, and more prone to collisions and mergers. Over time, these proto-galaxies merged to form the larger galaxies we see today. The James Webb Space Telescope has given us glimpses of these early galaxies, revealing their irregular shapes and intense star formation. They are like galactic building blocks, the raw materials from which today's universe was constructed. Looking at them is like seeing the universe in its adolescence, still growing, still figuring out what it would become. The universe has walls of galaxies. On the larger scales, galaxies aren't just scattered randomly. They form structures called galaxy walls or sheets, vast thin planes of galaxies stretching across hundreds of millions of light years. These walls surround enormous voids, creating a foam-like structure to the universe. The largest known structure, the Hercules Corona Borealis Great Wall, spans about 10 billion light-years. It's so large that light takes billions of years just to cross from one end to the other. These structures challenge our understanding of cosmic homogeneity. On small scales, the universe is clumpy, but on the very largest scales, it's supposed to be smooth. These walls exist at the boundary between clumpy and smooth, hints of the universe's deepest structure. Fast radio bursts are still mysterious. In 2007, astronomers discovered a new phenomenon, fast radio bursts, or FRBS. These are brief, intense pulses of radio waves lasting just milliseconds. They come from distant galaxies, and the energy released in that tiny fraction of a second is enormous, as much as the sun puts out in days. We still don't fully understand what causes them. Leading theories involve magnetaires, neutron star collisions, or other cataclysmic events. Some FRBs repeat, while others seem to be one-time events. They arrive without warning from random parts of the sky. They're one of the newest mysteries in astronomy, and solving them might reveal new physics or new types of cosmic phenomena. The Sun will eventually become a planetary nebula. In about 5 billion years, the Sun will run out of hydrogen fuel in its core. It will swell into a red giant, consuming Mercury and Venus, and possibly Earth. Eventually it will shed its outer layers, ejecting them into space in a beautiful expanding shell of glowing gas, a planetary nebula. At the centre will remain a white dwarf, the Sun's exposed core. The planetary nebula will fade over thousands of years, dispersing into the interstellar medium. The heavy elements created in the Sun's core will mix with the galaxy's gas, eventually becoming part of new stars and planets. The Sun's death will seed the cosmos with the building blocks of future worlds. Space can tear itself apart. There's a hypothetical end to the universe called the Big Rip. If dark energy continues to accelerate the expansion of the universe, and that acceleration increases over time, eventually even the fundamental forces holding matter together won't be able to resist it. First, galaxy clusters would be torn apart, then galaxies, then solar systems, then stars and planets. Eventually, even atoms would be ripped apart as space expands faster than the electromagnetic force can hold them together. The universe would end not in cold darkness, but in a violent, rapid tearing of the fabric of reality itself. It's one possible fate, though not the most likely based on current observations. But the fact that it's even possible shows how powerful and strange dark energy might be. Rogue black holes wander the galaxy. Just as there are rogue planets ejected from their star systems, there are likely rogue black holes wandering through the galaxy, unbound to any particular region. They could have been kicked out by gravitational interactions or left behind when their host galaxies were destroyed. These black holes are nearly impossible to detect unless they pass through gas or dust, creating a brief flare of radiation. But they're out there, invisible gravitational hazards drifting through space. A rogue black hole could pass through our solar system without us ever knowing, unless it happened to disturb a comet or asteroid and sent it on an unusual trajectory. The observable universe contains about 2 trillion galaxies early. Estimates put the number of galaxies in the observable universe at around 100 to 200 billion. But deeper surveys and better understanding have revised that number upward. Current estimates suggest about 2 trillion galaxies. Most of these are small, faint and distant. Each galaxy contains tens of millions to hundreds of billions of stars. The number of stars in the observable universe is therefore staggering, something like 10 to the power of 24, a trillion. And many of those stars have planets. The sheer scale of existence is beyond human comprehension, a reminder of how vast the universe is and how small our corner of it. The coldest place in the universe is on Earth. The coldest natural temperature in the universe is the cosmic microwave background radiation at about 2.7 Kelvin. But humans have created colder temperatures in laboratories. The coldest place ever recorded is in a lab, where physicists cooled atoms to just above absolute zero, billionths of a degree Kelvin. At these, temperatures matter behaves strangely. Atoms slow down to nearly a standstill. Quantum effects become visible on macroscopic scales. Substances can form Bose-Einstein condensates, where multiple atoms occupy the same quantum state and act as a single entity. We've created temperatures colder than anywhere else in the natural universe. Coldness so extreme that the familiar laws of physics start to blur. Some moons have subsurface oceans. Jupiter's moon Europa and Saturn's moon Enceladus both likely harbour vast oceans of liquid water beneath their icy crusts. These oceans are kept liquid by tidal heating. Gravitational flexing from their parent planets generates heat through friction. Plumes of water vapour have been detected erupting from Enceladus's surface, and Europa's surface shows cracks and ridges suggesting a liquid layer below. These subsurface oceans are some of the most promising places to search for extraterrestrial life in our solar system. They're protected from radiation, contain liquid water, and might have the right chemistry. If life exists elsewhere in the solar system, it might be swimming in these dark, hidden seas. The Sun's corona is hotter than its surface. The Sun's surface, or photosphere, has a temperature of about 5,800 Kelvin, but the Sun's outer atmosphere, the corona, is millions of degrees Kelvin. This is deeply counterintuitive. It's like holding your hand farther from a fire and feeling more heat, not less. The exact mechanism heating the corona is still debated. It likely involves magnetic fields and plasma waves transferring energy from the Sun's interior to its outer layers. Understanding coronal heating is one of the major unsolved problems in solar physics. The Parker Solar Probe is currently flying through the corona, gathering data that might finally explain this mystery. Galaxies without stars exist. In 2016, astronomers discovered a galaxy called Dragonfly 44 that appeared to be almost entirely made of dark matter. It's a large galaxy, about the size of the Milky Way, but contains very few stars, less than 1% of what a typical galaxy that size would have. It's essentially an invisible galaxy, detectable only by its gravitational influence. Since then, other ultra-diffuse galaxies have been found with similar properties. We don't fully understand how or why these galaxies form. They might be the remnants of larger galaxies that had their stars stripped away, or they might represent a different path of galaxy formation. They're ghostly structures, dark matter frameworks that somehow never filled in with the normal matter we expect. The pillars of creation are being destroyed. The famous pillars of creation in the Eagle Nebula, photographed by the Hubble Space Telescope, are vast columns of gas and dust where new stars are forming, but they're being eroded by radiation from nearby hot stars. Slowly, they're evaporating, the gas blown away into space. In fact, they may already be gone. The pillars are about 7,000 light-years away. If a supernova occurred near them 6,000 years ago, it would have destroyed them, but we won't see that destruction for another 1,000 years. We're seeing them as they were 7,000 years ago. They might already be a memory, and we're looking at ghosts. Space tastes sweet. If space had a taste, it might be sweet. In 2008, astronomers discovered glycolaldehyde, a simple sugar molecule, in a gas cloud near the centre of our galaxy. It's the same sugar found in RNA. Finding complex organic molecules like this in space isn't uncommon. Space is full of chemistry. Amino acids, the building blocks of proteins, have been found in meteorites and comets. The ingredients for life are surprisingly widespread. Space isn't just empty darkness. It's a vast chemical laboratory where the precursors of life drift and react. The universe is fertile, seeded with possibility. Some asteroids have their own moons. It's not just planets that have moons. Some asteroids have smaller asteroids orbiting them. These binary asteroids form either through capture or through rotational fission, where a rapidly spinning asteroid sheds material that settles into orbit. About 15% of near-Earth asteroids are binary systems. One asteroid, Ida, has a moon named Dactyl. It's tiny, just 1.4 kilometers across, but it orbits Ida like a miniature moon. These systems remind us that orbital dynamics work at all scales. Even a pile of rubble held together by weak gravity can capture a companion and become a small planetary system. The Sun is orbiting a black hole. At the centre of the Milky Way lies a supermassive black hole called Sagittarius, a star. It has a mass of about 4 million suns. Our entire solar system orbits this black hole, along with all the other stars in the galaxy. The Sun takes about 225 million years to complete one orbit. We're moving through space at about 230 kilometers per second, carried along by the galaxy's rotation. We've completed about 20 orbits since the Sun formed. The last time we were in this part of the galaxy, dinosaurs roamed the Earth. We're on a cosmic merry-go-round, endlessly circling the galactic centre. Some planets orbit backward. Most planets in our solar system orbit the Sun in the same direction the Sun rotates, counterclockwise when viewed from above the North Pole. But some exoplanets orbit in the opposite direction from their star's rotation. These retrograde orbits are puzzling. They might result from gravitational interactions with other planets, flinging a planet into an inclined orbit that eventually flips, or they might form in unusually chaotic disks where material orbits in different directions. Either way, they show that planetary systems can be messier and more diverse than our relatively orderly solar system. Volcanoes exist. Beyond Earth, Io, one of Jupiter's moons, is the most volcanically active body in the solar system. Its surface is covered with hundreds of active volcanoes, spewing sulfur and sulfur dioxide hundreds of kilometers into space. The volcanoes are powered by tidal heating from Jupiter's immense gravity. Mars has the largest volcano in the solar system, Olympus Mons, a shield volcano about 22 kilometers high, nearly 3 times the height of Mount Everest. Venus's surface is covered in volcanic features, and Saturn's moon Enceladus has ice volcanoes, or cryovolcanoes, that erupt water instead of lava. Volcanism is common in the solar system, shaping worlds in strange and alien ways. The universe may have no edge. If the universe is infinite, it has no edge. But even if it's finite, it might still have no edge if it curves back on itself, like the surface of a sphere. You could travel in a straight line forever and never reach a boundary. You'd just eventually return to where you started. We don't know which is true. Observations suggest the universe is either infinite or so large that any curvature is too subtle to measure. Either way, the idea of an edge, a place where space simply stops, doesn't seem to fit with what we know. Space doesn't have walls, it just is. Some stars explode. Twice. Certain massive stars don't explode once. They explode, collapse, and then explode again. These are called pair instability supernovae. They occur in extremely massive stars over 130 times the Sun's mass. As the star's core gets hotter, gamma rays in the core become so energetic that they spontaneously transform into electron-positron pairs. This removes pressure support, causing the core to collapse. The collapse triggers runaway fusion, tearing the star apart in a massive explosion. But instead of leaving a remnant, the explosion is so complete that it obliterates the star entirely. No neutron star, no black hole, just dispersed elements. These explosions are rare, but they may have been more common in the early universe when such massive stars were more prevalent. Dark energy might be a flaw in Einstein's equations. Dark energy is the name we give to whatever is accelerating the universe's expansion. It makes up about 68% of the universe's energy content. But we don't know what it is. One possibility is that it's a cosmological constant, a form of vacuum energy. Another possibility is that it's a dynamic field changing over time. But there's a third possibility. Dark energy might not exist at all. Maybe our equations are wrong. Perhaps general relativity breaks down on the larger scales. This seems unlikely given how well general relativity works everywhere else. But the universe has surprised us before. Dark energy remains one of the deepest mysteries in science. The Moon is drifting away. Every year, the Moon moves about 3.8 centimeters farther from Earth. This drift is caused by tidal interactions. The Moon's gravity creates tides on Earth, and as Earth rotates beneath these tidal bulges, friction gradually transfers rotational energy from Earth to the Moon's orbit, pushing it outward. Billions of years ago, the Moon was much closer. Days were shorter, tides were stronger. Eventually, in the far future, Earth and the Moon will become tidally locked, with the same sides always facing each other. The Moon will stop drifting away, and both will rotate in synchrony, frozen in their cosmic dance. Comets are time capsules. Comets are made of ice and dust, remnants from the solar system's formation. They've spent billions of years in the cold outer reaches, largely unchanged. When a comet falls into the inner solar system and we study it, we're examining material that dates back to the solar system's birth. The Rosetta mission landed on Comet 67P/Churyumov-Gerasimenko and found complex organic molecules, including some that are precursors to life. Comets may have delivered water and organic compounds to the early Earth, seeding the planet with the ingredients necessary for life. They're not just icy rocks, they're messengers from the past. Some exoplanets rain glass. On the exoplanet HD 189733b, the weather is extreme. Winds blow at 7,000 kilometers per hour, and the atmosphere contains silicate particles. When these particles condense, they form glass. The result is sideways rain made of molten glass shards, driven by hurricane-force winds. This planet is a hot Jupiter, orbiting very close to its star. The extreme heat and winds create conditions unlike anything in our solar system. Other exoplanets have similarly bizarre weather. Planets where it rains iron, where the atmosphere is thick with vaporized rock, or where diamond rain falls deep in the atmosphere. The diversity of worlds is astounding. The universe is beige. If you were to average the colour of all the light emitted by all the galaxies in the universe, what colour would you get? Astronomers did this calculation and found that the universe's average colour is a shade of beige. They even gave it a name, cosmic latte. It's not the most romantic's colour for the universe, but it reflects the mix of young blue stars and older red stars, combined with the full spectrum of light from all sources. As the universe ages and fewer hot blue stars form, the average colour will shift toward red. The universe is slowly fading from beige to brown, a cosmic autumn. Your atoms are immortal. Atoms don't die. They can be rearranged, bonded into new molecules, incorporated into new structures, but the atoms themselves persist. The atoms in your body have existed since shortly after the Big Bang. They've been part of stars, planets, oceans, and countless living things before you. After you die, those atoms will return to the earth, be taken up by plants, eaten by animals, washed into the sea. They'll continue their journey through the cosmos, perhaps one day becoming part of another person, another world. You are a temporary arrangement of eternal pieces, a pattern in the flow of matter through time. The sun will outlive Earth's habitabilities. Sun is gradually getting brighter as it ages. In about 1 billion years, it will be about 10% brighter than it is now. That might not sound like much, but it will be enough to trigger a runaway greenhouse effect on Earth. The oceans will evaporate. The surface will become too hot for liquid water or life as we know it. Long before the sun becomes a red giant and engulfs the inner planets, Earth will already be uninhabitable. If humanity or its descendants still exist by then, they'll need to find a new home. The cosmos is full of other stars, other worlds. The journey outward is not just exploration, it's survival. We're made of stardust. It's one of the most repeated facts in astronomy, but it's worth remembering. Every atom in your body heavier than hydrogen was forged in a star. The carbon, nitrogen, oxygen, calcium, iron, all created by nuclear fusion in stellar cores or in the explosive deaths of massive stars. You are literally stardust, organized into a form capable of contemplating the stars that made you. When you look up at the night sky, you're looking at your origin. The universe has become conscious through you, aware of itself. In this sense, we're not separate from the cosmos. We're part of it. The universe examining itself through billions of curious eyes. Black holes can evaporate. Stephen Hawking showed that black holes aren't completely black. Through a quantum effect near the event horizon, they emit a tiny amount of radiation called Hawking radiation. This radiation carries away energy, which means the black hole slowly loses mass. Over incredibly long timescales, this process can cause a black hole to evaporate completely. For a stellar mass black hole, the evaporation time is far longer than the current age of the universe, something like 10 to the power of 67 years. Small black holes evaporate faster, and if any microscopic black holes exist, they might evaporate quickly, ending in a burst of radiation. But for the black holes we know about, evaporation is so slow that it's effectively eternal. By the time they evaporate, the universe will be unrecognizably different. The Milky Way has cannibalized other galaxies. Our galaxy hasn't grown alone. It's consumed numerous smaller galaxies over its lifetime. We can see evidence of this cannibalism in streams of stars that arc through the galactic halo, remnants of dwarf galaxies torn apart by the Milky Way's gravity. The Sagittarius dwarf elliptical galaxy is currently being consumed. It's passing through the Milky Way's disk, losing stars with each passage. Eventually it will be completely absorbed, its stars, becoming indistinguishable from the Milky Way's own. This process of galactic cannibalism has helped the Milky Way grow to its current size, and it will continue as other small galaxies fall into its gravitational grip. The cosmic microwave background hums. The cosmic microwave background isn't perfectly uniform. It has tiny temperature fluctuations, hot and cold spots that differ by only millionths of a degree. These fluctuations represent sound waves in the early universe, acoustic oscillations in the hot plasma that filled space before atoms formed. When we map these fluctuations, we're seeing the frozen imprint of sound waves from when the universe was 380,000 years old. The pattern tells us about the composition and geometry of the universe. It's like looking at ripples on a pond and working backward to understand what caused them. The universe once hummed with sound, and we can still see the pattern of those ancient vibrations. Exoplanets outnumber stars. For centuries we wondered if other stars had planets. Now we know, most do. Current estimates suggest there are more planets than stars in the Milky Way. With roughly 200 to 400 billion stars in our galaxy, that means there could be 1 trillion planets or more. Many of these planets are nothing like Earth. Hot Jupiters orbit scorchingly close to their stars. Super-Earths are rocky worlds larger than our own. Mini-Neptunes have thick hydrogen atmospheres. The diversity is astounding. And among all these worlds, there might be millions or billions in the habitable zone where liquid water could exist. We're just beginning to explore this vast population of exoplanets. Pulsars can have planets. In 1992, astronomers detected the first confirmed exoplanets, but they weren't orbiting an ordinary star. They were orbiting a pulsar, a rapidly rotating neutron star. This was unexpected. Pulsars form in supernova explosions that should destroy any existing planets. These planets likely formed from the debris of the supernova itself, or from a companion star torn apart by the pulsar. They orbit in a harsh environment, bathed in intense radiation. No life as we know it could survive there, but their existence shows that planets can form in the most unlikely places, and that planetary systems are more diverse and resilient than we imagined. The largest volcano in the solar system is on Mars, Olympus. Mons on Mars stands about 22 kilometers high, nearly 3 times taller than Mount Everest. Its base is 600 kilometers across, roughly the size of Arizona. It's a shield volcano, built up over billions of years by countless lava flows. The volcano is so large because Mars has lower gravity than Earth and no plate tectonics. On Earth, the tectonic plate moves over the hotspot, creating a chain of volcanoes like the Hawaiian Islands. On Mars, the crust stays in place, allowing the volcano to grow continuously in one spot. Olympus Mons is probably extinct now, but it stands as a monument to Mars's more geologically active past. Some galaxies are loners. Most galaxies exist in groups or clusters, bound together by gravity. But some galaxies are isolated, floating in voids far from other large galaxies. These field galaxies evolve differently. Without the gravitational interactions that trigger mergers and disturb gas clouds, they tend to be quieter, with less active star formation. The Milky Way is part of the local group, which includes Andromeda and about 80 smaller galaxies. But in cosmic voids, a galaxy might have no significant neighbours within tens of millions of light-years. It's a lonelier existence, drifting through empty space with no companions. These isolated galaxies offer insights into how galaxies evolve in the absence of external influences. The Sun's core is as dense as lead. The Sun might appear as a glowing gas, but its core is incredibly dense. The immense pressure from the weight of all the layers above compresses the core to about 150 times the density of water, similar to the density of lead. At the same time, the temperature reaches 15 million degrees Kelvin. In these extreme conditions, hydrogen nuclei move fast enough to overcome their electric repulsion and fuse into helium, releasing energy. This fusion is what powers the Sun and creates the light and heat that sustains life on Earth. The core is a nuclear furnace, and the Sun is essentially a giant fusion reactor held together by its own gravity. Stars can be darker than they appear. Brown dwarfs are often called failed stars, but they're more like stars that couldn't quite make it. They're massive enough to fuse deuterium, a heavy form of hydrogen, but not massive enough to sustain regular hydrogen fusion. As a result, they shine dimly and cool over time. The coolest brown dwarfs have surface temperatures comparable to hot ovens, around 300 to 500 Kelvin. They're barely warm by stellar standards. Some might even have water vapour in their atmospheres. They're neither star nor planet, occupying their own category in the cosmic taxonomy. And they're surprisingly common, possibly outnumbering main sequence stars in the galaxy. Venus spins backward. Most planets in the solar system rotate in the same direction they orbit the Sun, but Venus is different. It rotates backward, a phenomenon called retrograde rotation. A day on Venus, one complete rotation, takes longer than a Venusian year. The planet completes an orbit around the Sun before it completes one rotation on its axis. Why Venus rotates backward is still debated. It might have been knocked over by a giant impact early in its history, or tidal interactions with the Sun might have gradually flipped its rotation over billions of years. Either way, Venus is an oddball, reminding us that planetary systems can be chaotic and unpredictable. Cosmic voids aren't truly empty. Cosmic voids are vast regions of space with very few galaxies. They're the empty spaces between the filaments and clusters in the cosmic web. But they're not completely empty. They contain some diffuse gas, dark matter, and a few isolated galaxies. These voids are growing as the universe expands. Galaxies are drawn toward filaments by gravity, leaving the voids even more empty. In billions of years, these voids will be vaster and darker, with their few remaining galaxies drifting farther and farther apart. Voids are the universe's quiet places, where the influence of gravity is weakest and expansion dominates. Stars can form, rings around supermassive black holes. At the center of many galaxies, stars orbit the supermassive black hole in surprisingly orderly patterns. In some cases, these stars form rings or disks, all orbiting in roughly the same plane. The stars can be young, having formed from gas that fell into the galactic center. It's remarkable that stars can form so close to a black hole. The tidal forces and intense radiation should make star formation difficult. Yet these stars exist, orbiting the black hole at tremendous speeds. Some complete an orbit in just years. They're living on the edge, dancing around the galaxy's most destructive object. Gravity travels at the speed of light. Just as light takes time to travel through space, so does gravity. If the Sun suddenly vanished, Earth wouldn't fly off into space immediately. It would continue orbiting for about 8 minutes, the time it takes for light or gravity to travel from the Sun to Earth. This was a key prediction of Einstein's general relativity. Gravity isn't a force transmitted instantaneously. It's the curvature of space-time, and changes in that curvature propagate outward as gravitational waves at the speed of light. When massive objects like black holes collide, the gravitational waves they create ripple outward, eventually reaching us, sometimes billions of years later. The universe may be one of many. Some theories suggest our universe isn't unique. In the multiverse hypothesis, our universe is just one bubble in a vast cosmic foam. Each bubble might have different physical laws, different constants of nature. In some universes, atoms might not form. In others, stars might not shine. We have no direct evidence for the multiverse, and it's unclear if we ever could. If true, it raises profound questions. Why do we exist in a universe suited for life? Perhaps because only in such universes could observers arise to ask the question. The multiverse is deeply speculative, but it's a reminder that even our vast universe might be just a small part of something incomprehensibly larger. Quasars outshine entire galaxies. Quasars are among the brightest objects in the universe. They're powered by supermassive black holes consuming gas at prodigious rates. The infalling material heats up and emits enormous amounts of radiation, sometimes more than 1 trillion times the Sun's luminosity. A single quasar can outshine its entire host galaxy. Because they're so bright, we can see quasars from enormous distances. Some of the most distant quasars we've observed existed when the universe was less than 1 billion years old. They're windows into the early universe, showing us how galaxies and black holes evolved in cosmic youth. Quasars were more common in the past. As the universe aged and galaxies used up their gas, quasars faded. Today, most galaxies have quiet central black holes, dormant compared to their quasar days. Saturn's rings are temporary. Saturn's magnificent rings are one of the solar system's most beautiful features, but they won't last forever. The rings are made of countless ice particles ranging from dust grains to house-sized boulders. These particles are gradually falling into Saturn's atmosphere, pulled by gravity and slowed by the planet's magnetic field. Scientists estimate that Saturn's rings might only last another 100 million years or so, a blink of an eye in cosmic terms. The rings might be relatively young, perhaps formed by the breakup of a moon or comet that wandered too close. In the far future, Saturn will be ringless, just another gas giant. We're fortunate to live in an era when Saturn has rings to admire. Some stars are fleeing the galaxy. Hypervelocity stars move fast enough to escape the Milky Way's gravity. They travel at speeds of 1,000 kilometers per second or more. Most likely got their speed from close encounters with the supermassive black hole at the galactic center. When a binary star system gets too close, the black hole can capture one star and fling the other outward at incredible speed. These stellar exiles will spend the rest of their lives crossing intergalactic space, never to return. They're rare, but we've found several dozen. Each one tells the story of a near miss with the galaxy's central black hole, a gravitational slingshot that sent it careening into the cosmic dark. The Moon stabilizes Earth's tilt. Earth's axis is tilted about 23.5 degrees relative to its orbit around the Sun. This tilt gives us seasons. But without the Moon's gravitational influence, Earth's tilt would vary chaotically over millions of years, causing wild climate swings. The Moon acts as a stabilizer, keeping Earth's tilt relatively constant. This stability has been crucial for life. Predictable seasons and a stable climate allowed complex ecosystems to develop. The Moon's influence extends beyond tides. It's helped create the conditions for life to flourish. In this sense, the Moon isn't just our companion in space. It's one of the reasons we're here. Fusion powers the stars. At the heart of every star is a nuclear furnace. The immense pressure and temperature in a star's core force hydrogen nuclei to fuse into helium. This process releases energy according to Einstein's E=mc². A small amount of mass is converted into a large amount of energy. This fusion energy radiates outward, creating the light and heat that stars emit. It's the same process that powers hydrogen bombs, but in a star it's controlled and sustained by gravity's steady pressure. When the hydrogen runs out, stars can fuse helium into heavier elements, carbon, oxygen, and so on. The most massive stars fuse elements all the way up to iron before they run out of fuel and explode. Space is expanding between the galaxies. The universe is expanding, but that doesn't mean galaxies themselves are getting bigger or stars are moving apart. It means the space between galaxy clusters is stretching. Within a galaxy or galaxy cluster, gravity is strong enough to hold things together despite expansion. But on the larger scales, where gravity is weaker, expansion dominates. Distant galaxies are receding from us not because they're moving through space, but because space itself is growing. The farther away something is, the faster it appears to recede, a relationship called Hubble's law. This expansion is one of the most profound discoveries in astronomy, revealing that the universe has a history and a future. Mercury has ice. Mercury is the closest planet to the Sun, with daytime temperatures hot enough to melt lead. But at its poles, in permanently shadowed craters, temperatures drop low enough for water ice to exist. Radar observations have confirmed that ice is present in these dark regions protected from the Sun's heat. This ice probably came from comet impacts over billions of years. It's one of the solar system's ironies, ice on the hottest planet. It also suggests that water might be more common throughout the solar system than we once thought, found in unexpected places waiting to be discovered. Galaxies rotate but don't fly apart. If you measure how fast stars orbit in a galaxy and calculate the mass needed to hold them in orbit, you get an answer much larger than the visible mass. Stars in the outer regions of galaxies move too fast. They should fly off into space, but they don't. This is one of the key pieces of evidence for dark matter. There's extra mass we can't see, providing the gravity needed to hold galaxies together. Dark matter forms a halo around galaxies, extending far beyond the visible disk. Without it, galaxies would disintegrate. Dark matter is the glue holding the universe's structures together. Jupiter is a failed star. Almost Jupiter is often called a failed star, but that's not quite accurate. It would need to be about 80 times more massive to sustain hydrogen fusion. Still, Jupiter does emit more heat than it receives from the Sun, radiating energy left over from its formation. In some ways, Jupiter is like a miniature solar system. It has at least 95 moons, its own magnetic field, and complex weather systems. If it were just a bit more massive, it might have ignited into a brown dwarf. But as it is, Jupiter remains a planet, the largest in our solar system, but still far from becoming a star. The speed of light is not infinite. For most of human history, people assumed light travelled instantaneously, but in 1676, Danish astronomer Ole Romer showed that light has a finite speed by observing the timing of eclipses of Jupiter's moons. Today, we know light travels at about 300,000 kilometers per second in a vacuum. This speed limit has profound implications. It means we can't see the universe as it is right now. We see distant objects as they were in the past. It also means that faster-than-light travel, as depicted in science fiction, seems impossible according to our current understanding of physics. The speed of light is woven into the fabric of space-time itself. Some asteroids are rubble piles. Not all asteroids are solid rocks. Many are rubble pile asteroids, loose collections of rocks, boulders and dust held together weakly by gravity. They're the remnants of ancient collisions, fragments that never quite coalesced back into a single solid body. These rubble piles are surprisingly resilient. If you tried to destroy one with an explosion, you might just scatter the pieces temporarily. They drift back together over time, held by their mutual gravity. This makes potentially hazardous asteroids harder to deflect than solid rocks. Understanding their structure is crucial for planetary defense. The universe has background neutrinos. Just as the cosmic microwave background is a relic from when the universe became transparent to light, there should be a cosmic neutrino background from even earlier times. Neutrinos are ghostly particles that barely interact with matter. They were created in the early universe and have been streaming through space ever since. We haven't directly detected this neutrino background yet. Neutrinos are notoriously difficult to detect. But theory predicts they're there, filling the universe, passing through us constantly. In fact, about 1 trillion neutrinos from the Big Bang pass through your body every second. They're a hidden component of the cosmos, a whisper from the universe's first moments. Stars can be twins. Many stars don't form alone. They form in pairs or even triplets, born from the same collapsing gas cloud. These binary or multiple star systems orbit their common center of mass. Some binaries are so close their surfaces almost touch. Others are separated by vast distances. About half the stars in the Milky Way are in binary systems. Our Sun is an exception, a solitary star. But elsewhere in the galaxy, most stars have companions. In some binary systems, the stars eventually interact dramatically, one star stealing material from the other, triggering novae or even supernovae. Binary stars remind us that stellar lives are often intertwined. The asteroid belt is mostly empty. Despite how it's depicted in movies, the asteroid belt between Mars and Jupiter isn't a dense field of rocks. The asteroids are spread over such a vast volume that spacecraft can pass through without much risk of collision. If you were standing on one asteroid, the next one would be so far away you'd likely not even see it with your naked eye. The total mass of all asteroids in the belt is less than the Moon's mass. Most of that mass is contained in just 4 large objects: Ceres, Vesta, Pallas, and Hygeia. The asteroid belt is a sparse region, a graveyard of planetary formation where Jupiter's gravity prevented material from coalescing into a planet. Titan has lakes and seas. Saturn's largest moon, Titan, is the only world besides Earth known to have stable liquid on its surface. But Titan's lakes and seas aren't made of water. They're filled with liquid methane and ethane, hydrocarbons that are gaseous on Earth but liquid in Titan's frigid environment. Titan has a thick atmosphere, clouds, rain, and river channels. It has a hydrological cycle, just like Earth's water cycle, but with methane. It even has waves on its seas, though they're small and gentle. Titan is one of the most Earth-like worlds in the solar system, despite being utterly alien in its chemistry. The vacuum of space can boil your blood. In the vacuum of space, without a spacesuit, you'd lose consciousness in about 15 seconds due to lack of oxygen. But you wouldn't explode, and your blood wouldn't boil in the traditional sense. However, the fluids in your tissues would vaporize, causing swelling. The lack of pressure would cause dissolved gases in your blood to form bubbles, similar to the bends that divers experience. You'd survive for a minute or two before dying from asphyxiation. It's not a pleasant way to go, but it's not as instantly catastrophic as movies suggest. Space is lethal, but humans are surprisingly resilient, at least for a short while. There's a giant hexagon on Saturn. At Saturn's north pole, there's a persistent hexagonal cloud pattern larger than Earth. The hexagon has been observed for decades, and it rotates with the planet. Each side of the hexagon is about 13,800 kilometers long. The hexagon is thought to be a type of standing wave in Saturn's atmosphere, possibly related to jet streams. Similar patterns can be created in laboratory experiments with rotating fluids, but seeing such a geometric shape in a planetary atmosphere is bizarre and beautiful. Saturn's hexagon is a reminder that nature can create patterns, more precise than we might expect from chaotic systems. Red giants can swallow their planets. When a star like the Sun exhausts the hydrogen in its core, it begins fusing hydrogen in a shell around the core. This causes the outer layers to expand dramatically. The star becomes a red giant, hundreds of times larger than before. As the Sun becomes a red giant in about 5 billion years, it will likely engulf Mercury and Venus. Earth might survive, pushed into a wider orbit by the Sun's mass loss, or it might be consumed as well. Either way, Earth will be scorched and uninhabitable. The inner solar system will be transformed, the planet's fate sealed by their star's aging. Galaxies can be transparent. Most galaxies appear solid and opaque in photographs, but that's an illusion created by countless overlapping stars. In reality, galaxies are mostly empty space. If you were inside a galaxy, the distances between stars are so vast that you could see straight through to the other side in most directions. Even in the densest regions, like the galactic center, collisions between stars are extremely rare. Galaxies are ghostly structures, held together by gravity but sparse in substance. When two galaxies collide, their stars pass through each other largely unscathed. It's the gas clouds that collide, triggering bursts of star formation. The Milky Way is warped. The Milky Way's disk isn't perfectly flat. It's warped and twisted at the edges, like a vinyl record left in the sun. This warping is likely caused by gravitational interactions with satellite galaxies, particularly the Magellanic Clouds. The warp is subtle, but measurable. Different parts of the galaxy's disk are tilted at slightly different angles. Understanding this warp helps astronomers map the galaxy's structure and mass distribution. It's a reminder that even our home galaxy is dynamic, constantly shaped by the gravitational dance of the cosmic neighborhood. Space isn't perfectly dark. Even in the darkest parts of space, far from any stars, there's a faint glow, called the zodiacal light. It's caused by sunlight reflecting off dust particles in the solar system. There's also a similar glow from outside the solar system, starlight scattered by interstellar dust. The universe has a dim, persistent background glow from all these sources combined. Space isn't pitch black. It's more like a dimly lit room. Your eyes, given time to adjust and no atmosphere to scatter light, might see this faint luminosity. Space has a quiet radiance, a soft twilight that never ends. The sun has weather. The Sun isn't a static ball of fire. It has complex weather patterns, though nothing like Earth's. Solar flares erupt from the surface, releasing tremendous amounts of energy in minutes. Coronal mass ejections hurl billions of tons of plasma into space. Sunspots appear and disappear, marking regions of intense magnetic activity. These solar phenomena follow an 11-year cycle, with periods of high and low activity. During solar maximum, the Sun is covered with sunspots and prone to energetic eruptions. During solar minimum, it's quieter. This solar weather affects Earth, causing auroras, disrupting satellites, and even influencing our power grids. We're connected to our star in ways we're only beginning to understand. Some planets have backward moons. Most moons orbit in the same direction their planet rotates. But some moons have retrograde orbits, circling their planet in the opposite direction. Neptune's largest moon, Triton, is retrograde. It likely didn't form with Neptune but was captured from the Kuiper Belt. Captured moons often have unusual orbits, retrograde, highly elliptical, or inclined at odd angles. They're immigrants, not native to their planetary systems. Their presence tells stories of gravitational encounters and cosmic chaos. In the early solar system, things weren't as orderly as they are now. Stars can form from collisions. When galaxies collide, their gas clouds smash together, triggering intense bursts of star formation. The compression from the collision creates regions dense enough for gravity to collapse them into new stars. These starburst galaxies can form stars hundreds or thousands of times faster than the Milky Way currently does. The resulting stars are often massive and short-lived. They burn bright blue for a few million years before exploding as supernovae. In time, the starburst fades, and the galaxy settles into a quieter state. But for a brief cosmic moment, the collision lights up the universe, turning chaos into creation. Uranus rotates on its side. Most planets spin more or less upright relative to their orbit, but Uranus is tilted 98 degrees, essentially rotating on its side. This means Uranus's poles alternate between 42 years of continuous sunlight and 42 years of continuous darkness. The tilt was likely caused by a massive collision early in the solar system's history. Something planet-sized struck Uranus, knocking it over. The moons of Uranus orbit around its equator, tilted along with the planet. It's one of the solar system's most dramatic scars, a permanent record of ancient violence. The cosmic distance ladder. Measuring distances in space is one of astronomy's fundamental challenges. We use a series of methods called the cosmic distance ladder. For nearby objects, we use parallax, measuring how a star's position shifts as Earth orbits the Sun. For more distant objects, we use standard candles like Cepheid variables or supernovae, whose true brightness we know. Each method reaches farther but depends on calibrating the method below it. The cosmic distance ladder is how we've mapped the universe, measuring distances from neighbouring stars to galaxies billions of light years away. Any error in one rung affects all the rungs above it, which is why astronomers work so hard to refine each measurement technique. Black holes can create jets. Some black holes don't just swallow everything that comes near, they create powerful jets of matter and energy that shoot out from near the poles at nearly the speed of light. These jets can extend for millions of light years, far beyond the galaxy hosting the black hole. The jets are formed by magnetic fields twisted and amplified by the spinning black hole and its accretion disk. They're among the most powerful phenomena in the universe, capable of influencing the evolution of entire galaxy clusters. Ironically, the darkest objects in the universe can also create some of the brightest and most energetic displays. The Earth's atmosphere extends beyond the Moon. Earth's atmosphere doesn't end at the edge of space. It has an extended outer layer called the geocorona, made of extremely thin hydrogen gas. This layer extends beyond the Moon's orbit, about 630,000 kilometers from Earth. The Moon actually orbits within Earth's outer atmosphere, Of course, the geocorona is so tenuous that it's essentially a vacuum by any practical measure. But technically, the Moon is passing through Earth's atmosphere on every orbit. It's a reminder that boundaries in space are often fuzzy and arbitrary. There's no sharp line where atmosphere ends and space begins. Pulsars were mistaken for alien signals. When Jocelyn Bell discovered the first pulsar in 1967, the regular pulses were so precise that she and her colleagues jokingly called the source LGM1 for Little Green Men. They seriously considered whether the signals might be from an extraterrestrial civilization. But as more pulsars were discovered from different parts of the sky, it became clear they were natural phenomena, rapidly rotating neutron stars. Still, that initial moment of uncertainty shows how unexpected the universe can be. Sometimes reality is stranger than the explanations we invent. Some galaxies are invisible light. Ultra-diffuse galaxies are so faint and spread out that they're nearly invisible in optical wavelengths. They have the mass of typical dwarf galaxies but spread over a much larger volume, making them extremely low in surface brightness. Some weren't discovered until recently despite being relatively nearby. These dim galaxies challenge our surveys of the universe. How many galaxies have we missed simply because they don't shine brightly enough? The invisible galaxy population might be much larger than we thought, hiding in plain sight, too faint for our telescopes to easily detect. Lightning happens on other planets. Lightning isn't unique to Earth. It's been detected on Jupiter, Saturn, and possibly Venus. On Jupiter, lightning bolts can be thousands of times more powerful than those on Earth. They're created by the same process, colliding ice particles in clouds creating electrical charge separation. But the details differ. Jupiter's lightning happens in water clouds, similar to Earth. Saturn's lightning happens in deeper ammonia water clouds. Venus's lightning might be triggered by volcanic eruptions. Each planet puts its own spin on this electrical phenomenon, creating storms alien to our experience. The Milky Way is moving. The Milky Way isn't stationary. It's falling toward the Virgo cluster, a collection of galaxies about 50 million light-years away. But it's also being influenced by more distant structures, pulled in multiple directions by various gravitational attractors. Our local group of galaxies, the Milky Way, Andromeda, and their satellites, is moving at about 630 kilometers per second relative to the cosmic microwave background. That's our motion through the universe, our drift across cosmic space. Even as we orbit within the galaxy itself is on a journey, pulled by invisible masses across vast distances. Some comets visit once and never return. Most comets follow elliptical orbits, returning periodically to the inner solar system, but some comets are on hyperbolic trajectories, moving so fast that after they swing around the Sun, they escape the solar system entirely. These comets may have been accelerated by close encounters with planets, or they might be visitors from interstellar space. Interstellar comets, like Oumuamua and Borisov, are tourists passing through. They formed around other stars and were ejected from their home systems. They travel through interstellar space for millions or billions of years before briefly visiting our solar system and then departing, never to return. Each one is a messenger from another stellar neighborhood. Auroras occur on other planets. The northern and southern lights aren't unique to Earth. Any planet with a magnetic field and an atmosphere can have auroras. Jupiter's auroras are enormous, larger than Earth. Saturn has ultraviolet auroras at its poles. Even Mars, which has only a weak remnant magnetic field, has localized auroras over ancient magnetic regions in its crust. Auroras are created when charged particles from the solar wind interact with a planet's magnetic field and atmosphere, exciting atoms that then emit light. Each planet's auroras have unique characteristics depending on its atmospheric composition and magnetic field structure. They're a universal phenomenon, appearing wherever magnetic fields guide charged particles into atmospheres. The largest known structure is a galactic filament. The largest single structure in the observable universe is the Hercules Corona Borealis Great Wall, a galactic filament spanning about 10 billion light-years. It's so large that light takes billions of years to cross from one end to the other. This structure challenges theoretical predictions about cosmic homogeneity. According to cosmological principles, the universe should be relatively uniform on the largest scales. Structures larger than a certain size shouldn't exist, yet this filament exists, suggesting either our theories need refinement or that the universe has surprises we haven't fully accounted for. Moons can have atmospheres. Jupiter's moon has a thin atmosphere of sulfur dioxide created by its intense volcanic activity. Saturn's moon Titan has a thick nitrogen atmosphere, denser than Earth's. Even Pluto, technically a dwarf planet, has a tenuous atmosphere that freezes and falls to the surface as Pluto moves away from the Sun in its orbit. Moons with atmospheres are relatively rare, but they exist. An atmosphere requires either active geology to replenish gases lost to space, or enough gravity to hold on to an atmosphere for geological timescales. Some moons have both. These worlds blur the line between moons and planets, showing that size and position aren't the only factors that matter. The CMB has hot and cold spots. The cosmic microwave background isn't perfectly uniform. It has temperature variations of about 1 part in 100,000, tiny hot and cold spots across the sky. These fluctuations are the seeds of all structure in the universe. Slightly denser regions in the early universe attracted more matter, eventually forming the galaxies and galaxy clusters we see today. By studying the pattern of these fluctuations, cosmologists can determine the age, composition, and geometry of the universe. The CMB is a baby picture of the cosmos, showing us what things looked like just 380,000 years after the Big Bang. Everything that came later, stars, galaxies, planets, life, grew from those tiny variations. Stars can be magnetically connected. In some binary star systems, the magnetic fields of the two stars can interact, forming a kind of bridge between them. Plasma flows along magnetic field lines from one star to the other. In extreme cases, the stars can exchange material through this magnetic connection, affecting their evolution. These interactions can create complex light curves and unusual spectra. They're a reminder that stars aren't isolated objects. When they're close enough, they can influence each other in surprising ways, coupled not just by gravity but by magnetic forces that span the space between them. The universe was once opaque. Before the cosmic microwave background was released, the universe was opaque. Photons couldn't travel far without scattering off free electrons. It was like trying to see through a thick fog. Only when the universe cooled enough for atoms to form did it become transparent. This transition, called recombination, marked the moment when light could finally travel freely through space. Before that, there was no darkness and no light as we know it, just a glowing fog filling everything. The universe had to clear before stars could shine against a dark sky. The darkness we see between stars is a gift from cosmic expansion and cooling. Some galaxies are incredibly old. Some galaxies formed within the first billion years after the Big Bang. They're among the oldest structures in the universe. The James Webb Space Telescope has observed galaxies that existed when the universe was only a few 100 million years old, revealing what the cosmos looked like in its infancy. These early galaxies are smaller and more irregular than modern galaxies. They're undergoing intense star formation, building the first generations of heavy elements. Observing them is like looking at baby pictures of galaxies, showing us how they've grown and evolved over billions of years into the majestic structures we see nearby today. Black holes can hibernate. Not all supermassive black holes are actively consuming matter. Many are dormant, surrounded by empty space with nothing nearby to feed on. The Milky Way's central black hole, Sagittarius A star, is relatively quiet right now, emitting only a faint glow from sparse infalling matter. But these black holes can wake up. If a gas cloud wanders too close, or a star is torn apart by tidal forces, the black hole suddenly flares to life, emitting intense radiation as matter spirals inward. Then, when the meal is finished, it goes quiet again. Black holes alternate between active and dormant phases, their appetite dependent on what happens to drift within reach. The solar wind never stops. The sun constantly streams particles into space, a flow of charged particles called the solar wind. This wind extends far beyond the planets, creating a bubble around the solar system called the heliosphere. At the heliosphere's edge, the solar wind meets the interstellar medium, the thin gas between stars. Voyager 1 and 2 have both crossed this boundary, entering interstellar space. They've confirmed that the solar wind creates a protective bubble, shielding the inner solar system from some galactic cosmic rays. Without the sun's constant outflow, Earth would be exposed to higher levels of radiation. The solar wind is more than just particles streaming through space. It's our star's protective breath. Mars once had rivers-dried river valleys, lake beds, and minerals that form in water all point to one conclusion. Mars once had liquid water flowing on its surface. Billions of years ago, Mars was warmer and wetter with a thicker atmosphere. Rivers carved channels into the landscape. Lakes pooled in craters. But Mars lost most of its atmosphere, possibly stripped away by the solar wind after its magnetic field weakened. As the atmosphere thinned, liquid water could no longer exist on the surface. It either froze into the polar ice caps and subsurface ice, or evaporated into space. Mars today is a desert, but it's a desert that remembers water. Galaxies can be disrupted by tides. When a small galaxy passes close to a large one, the large galaxy's gravity pulls harder on the near side of the small galaxy than the far side. This difference in gravitational pull, called a tidal force, can stretch and distort the small galaxy, eventually tearing it apart. We see tidal streams around the Milky Way, long arcs of stars that were once part of dwarf galaxies. These streams trace the paths of galaxies that came too close and were shredded by the Milky Way's gravity. Tidal disruption is one way large galaxies grow, not through dramatic collisions, but through gentle cannibalism, one small galaxy at a time. The Hubble constant measures expansion. The Hubble constant tells us how fast the universe is expanding. It's measured by observing how quickly distant galaxies are receding from us. But here's the puzzle. Different measurement methods give slightly different values for the Hubble constant. This discrepancy is called the Hubble tension. One method uses the cosmic microwave background and early universe physics. Another uses nearby supernovae and variable stars. They should agree, but they don't, at least not perfectly. This tension might be a measurement problem, or it might hint at new physics we don't understand yet. It's one of cosmology's most pressing mysteries. Some stars pulse like heartbeats. Certain stars expand and contract rhythmically, pulsing in brightness. Cepheid variable stars are one example. They brighten and dim over days or weeks in a regular cycle. The period of pulsation is directly related to the star's luminosity. Brighter stars pulse more slowly. This relationship makes Cepheids valuable for measuring distances. By timing their pulsation, we know their true brightness, and by comparing that to their apparent brightness, we can calculate their distance. Cepheids were key to discovering that the universe is expanding. Henrietta Leavitt discovered their period luminosity relationship, and Edwin Hubble used it to show that spiral nebulae were actually distant galaxies. The universe might be curved. General relativity allows for three possible geometries of the universe: flat, open, negatively curved, or closed, positively curved. In a closed universe, space curves back on itself like the surface of a sphere. If you travelled in one direction long enough, you'd eventually return to your starting point. Current measurements suggest the universe is very close to flat, within observational uncertainty. But we can't rule out slight curvature. If the universe is closed, it's so large that any curvature is undetectable over observable distances. Whether flat or curved, the universe's geometry determines its ultimate fate: eternal expansion or eventual collapse. Neutron stars can glitch pulsars. Rotating neutron stars occasionally speed up suddenly. These events are called glitches. They're caused by the star's internal structure shifting. Neutron stars have a solid crust, but beneath it lies a superfluid, a frictionless fluid that doesn't rotate at the same speed as the crust. Occasionally, the superfluid transfers angular momentum to the crust, causing the star to spin faster. The glitch is sudden, increasing the rotation rate by a tiny fraction. Over time, friction slows the star back toward its pre-glitch speed. These glitches offer a window into the exotic physics inside neutron stars, where matter behaves in ways we can't replicate on Earth. Venus has longest days. A day on Venus, one complete rotation, lasts 243 Earth days. That's longer than a Venusian year, which is only 225 Earth days. Venus rotates so slowly that it completes an orbit around the Sun before it completes one rotation on its axis. Combined with its retrograde rotation, this creates bizarre day-night cycles. If you could stand on Venus's surface and look up through the dense clouds, you'd see the Sun rise in the west and set in the east, taking months to complete its journey across the sky. Venus is a planet where time moves strangely, out of sync with the rest of the solar system. The universe's elements were cooked in stars. Hydrogen and helium were created in the Big Bang, but almost everything else, the carbon in your body, the oxygen you breathe, the iron in Earth's core, was forged inside stars. Stars create heavier elements through nuclear fusion, and when they die, especially in supernova explosions, these elements are scattered into space. Over generations, gas clouds enriched with these elements collapse to form new stars and planets. Our solar system is made from the remnants of earlier stars. We're literally made of star stuff, assembled from atoms that went through stellar furnaces billions of years ago. The universe has a chemical memory, passing elements from one generation to the next. Goodbye for now. We've travelled far tonight. From the cold voids between galaxies to the hearts of dying stars. From rogue planets drifting alone to the elegant spiral of our own Milky Way. We've glimpsed mysteries both solved and unsolved, marvelled at the scale of existence, and remembered our own small but precious place within it. Wherever you are right now, whether still awake or drifting toward dreams, I hope you feel a little more connected to the cosmos. The universe is vast beyond imagining, but you're part of it. Your atoms have journeyed across space and time. Your consciousness is the universe wondering about itself. Sleep well. Dream of stars. And if you'd like to continue exploring the night sky with us, consider subscribing to Late Space. There are always more mysteries to uncover, more wonders to contemplate, more quiet moments under the stars. Until next time, rest easy. The universe will be here when you wake, patient and eternal, waiting for you to look up once more. Thank you for spending this time among the stars.